As with all things in Chapter 5, once we learn a new definition like independent, then we get to learn a new probability rule. So this is the multiplication rule for n independent events, and I want to make a few notes about it. First of all, I want you to note that this rule is going to be a rule that we use whenever there are multiple events happening at once. In other words, whenever there are multiple events. So if you have 2 things happening or 3 things happening, this is the one that we're going to use. Next, there was a bit of a typo. It should be events EI. I'll fix that for future semesters. But it's basically saying, hey, if you want the probability that event 1 happens and event 2 happens and then event 3 happens and then event 4 happens and so on, what you do is you multiply the probability of event 1 times the probability of event 2 times the probability of event 3 and so on. Keep in mind that these events are happening in an order. There's an order to this. There's first this, then this, then this. All right, so suppose you have the standard deck of cards, which we've been working with decks of cards for all these examples in Chapter 5. And you want to draw 2 cards at random. Now that's key. Once you see this in the setup, and the way the problem is written, you can tell, oh, hey, more than one thing is happening at once. I'm drawing 2 cards, or I'm drawing 3 cards, or I'm drawing 5 cards. We have not had that up to this point. If you look at the previous sections, it was always drawing a single card. But this is going to be when you're doing multiple events at the same time. Things like you toss the coin 4 times, you spin the roulette wheel 7 times, things like that. All right, so once I see the 2, I know it's going to be the multiplication rule. And I also see that it's with replacement. All of these are with replacement because that's what lets them be independent. If they were not with replacement, that would not be independent, and that's actually a different section. That's section 5.4. So multiple events. So it's these 2 things put together. It's multiple events with replacement. So they're independent. Which is good because we want to be able to use the independent rule up above, the multiplication rule for independent events. Okay, so suppose we're going to draw these 2 cards at random with replacement. Lovely. What is the probability that the first one is an ace and the second one is a heart? Notice there's an order here. There's a sequence. All right, so I want the probability of first the ace and then second is a heart. According to this, since ace and hearts are going to be independent because we replace the card, it will just be the probability of an ace times the probability of a heart. Now the probability of an ace is 4 out of 52. The probability of a heart is 13 out of 52. Now when you multiply, multiplication is not like adding. When you multiply the numerator times the numerator and the denominator times the denominator. So 4 times 13 is 52. 52 times 52 is 2,704, although I can prove it. So 4 times 13, 52 times 52 is 2,704, like I said, which leads me to 52 divided by 2,704, which is 0.0192. It's also 1 out of 52, if you want to see the fraction. All right, so this is 1 out of 52, which is approximately 0.0192. Usually we use the decimals on these, but in case they ask for the fraction, there you have it. All right, now suppose I'm drawing 2 cards again with replacement, so it's still a multiplication rule independent event. What is the probability that both of them are queens? Now, both is a key word that we're going to come back to later on in the page, so I'm just going to highlight it for now and I guess I'll choose green. So let's just kind of take a notice that. All right, so the probability that both are queens is the probability of a queen for the first card times the probability of a queen for the second card, which is 4 out of 52 times 4 out of 52. Because they were replaced, there's always 52 cards in the deck. 4 times 4 is 16. 52 times 52 is 2,704. Now, in Desmos, you have the option. You can say what 4 times 4 is and find that, but you can also do 4 divided by 52 times 4 divided by 52 and get a decimal, which is 0.0059, and you can also get a reduced fraction, which is 1 out of 169. So either way works. There we have it. And again, usually we would want decimals for these because, as you can see, the fractions get a little out of control. And also, decimals are easier because Desmos will just do them for you. Now we're going to kick it up a notch, or a couple notches actually. We want to draw 3 cards at random. And what is the probability that none of them are face cards? None. All right, well, that's a tricky business because I don't want the first one to be a face card. I don't want the second one to be a face card. I don't want the third one to be a face card. So the first thing I need to do is figure out, hey, what's the probability of a face card? So let me just start with that. So none is a little strange. None needs kind of the complement rule and the multiplication rule. So I'm going to make a little note of that. None means you're going to need complement rule and multiplication rule. So you need rule number 3 and rule number 4. I'll show you what I mean. Okay, so the first thing I want to do is I want to find the probability of not being a face card. So I guess to do that, I want to start off with the probability of a face card. So the probability of a face card is 12 out of 52. So the probability of not a face card would be 1 minus 12 out of 52, which is 52 out of 52, right? Take the 52 card deck, take away the 12 face cards, and you've got 40 out of 52. All right, now how does this help me? What are we talking about? Well, this is only for one card, right? So this is for one card. This is review. This is the complement rule, right? So this is rule number 3. So now I want to use rule number 5, rule number 4, and I want to talk about 3 cards. Okay, for 3 cards, I want the probability of no face cards out of 3. So that means I want the probability the first card is not a face times the probability that the second card is not a face times the probability the third card is not a face. This is the way none works. So none is a little tricky. For none, you got to find the probability of the complement, not a face, and then you multiply it. So you're going to take 40 out of 52 times 40 out of 52 times 40 out of 52. And you're going to multiply them all, right? So if you will, it's 40 out of 52 cubed. I'm not even going to bother finding the fraction. This is what Desmos is for. So I can do 40 out of 52. So let me show you. Well, first of all, let me just prove. 52 take away 12 was 40. So that's where that came from. So I could take 40 out of 52 times 40 out of 52 times 40 out of 52. Or if you like, you could take parentheses 40 divided by 52 to the third power. And I'm doing that with Shift 6. It's the caret button. You can also do it with the A to the B button out here. So if I hit A to the B, I can make that power up there, and then I can hit third. There you go. So 0.4552. I will tell you, be careful when you do this. I'll just do this wrong real quick. If you just type 3, that's multiplying by 3. Right? You can kind of tell because the 3 is a little bit larger and it's kind of in line with the middle line of the fraction. When it's a power, it should be up a little bit higher, up there. And that's how you can tell. So this one's wrong and that one's correct, 0.4552. If you're worried about it, you can just type the fractions. All right, 0.4552. I just squeezed it in there. That's one of the harder ones, so you might want to star it. None is actually deceptively difficult. You would think none would be easy, but it's not. All is actually pretty easy. All is, I want all of them to be hearts. So you just take the probability of heart and you multiply it by itself 5 times. So the probability that all are hearts is the probability of heart times the probability of heart. You're just multiplication rule right out. There's no complement rule, no nothing. The reason the one above has the complement rule is because of the none. That word is negative. It's a negative connotation, so it's a complement. So in other words, I'm taking the probability of heart to the 5th power. All right, so what was the probability of heart? Well, it's 13 out of 52, or 1/4, if you will. So it's 13 out of 52 times 13 out of 52. And you have to do it 5 times because there's 5 cards being drawn. If it was 4 cards, I would stop right there, but it's 5 cards. And of course, this is much easier to do just in a fraction like this. And of course, if you're thinking, well, that's the same thing as 1/4 to the 5th power, sure it is. That's fine too, right? So let me grab Desmos. So I could say 13 out of 52 to the 5th power, right there, 0.00097, right? Or you could sit there and do 13 out of 52 times 13 out of 52 times 13 out of 52 times 13 out of 52, and so on. Okay, so we get that it's 0.000976. Now, if you're going to go to 4 decimal places, that 7 rounds that 9 up to a 10. So if you're doing 4 decimal places, this would actually be 10 like that. Or if you will, 0.001. We never have to put a last 0 on it. All right, so a couple things. One, this is great. This multiplication rule is really great because it means that I don't have to do this giant tree diagram. I mean, think about it. For 5 cards, what a huge tree diagram that would be, right? 52 branches every time. So we don't have to do a tree diagram. We technically don't have to assume equally likely. These probabilities can work out even if they're not equally likely, and we don't have the nightmare of tree diagrams. Great. But more importantly, we've learned that there are words in English that hide a multiplication rule. So and is hidden in other words like both, all, right? We saw both of these, right? Both was letter B, all was letter D, none, 2 of them, 3 of them. I want 3 hearts and 4 hearts and things like that. That's multiplication rule. Now the trickiest of these is none. So I'm just going to make a little note about none. For none, what you have to do is you have to find the probability of, let's say if you want none of event E. Let me just write it this way. What you have to do is find the probability of not E. Oh, E. I made that capital E. I made it lowercase for no reason. All right, sorry, hold on. Gotta fix it. Not E. And then you raise it to the n power, right? Which if you look at it, that's what we did. We found the probability of not face, which was 40 out of 52, and then we raised it to the 3rd power because that's how many cards we were drawing, right? So you take the probability of not what you were looking for and raise it to the e power, or to the n power. I wasn't happy with the way my whiteout was messing with things, so I just rewrote it. All right, so none is a very tricky one. So the rest of these aren't actually that tricky. You just take the probability and multiply, no problem. But none is a little weird because you have to find the probability first with the complement rule. So the probability of not E is this bit inside. So you have to find that bit with the complement rule and then raise it to the power that you're looking for. All right, so just be careful of those.